and welcome to the Birch Aquarium. I am Nigella Hilgarth, the Executive Director of the Birch Aquarium at Scripps. It's my great pleasure this evening to introduce our speaker, Dr. Ed Parnell. He was born and raised here in San Diego and has been fascinated by marine life ever since he was given a mask and a snorkel when he was 4 years old, and he jumped into the children's pool in La Jolla and hasn't looked back since, I gather. In fact, he used to take the bus from North Park, where his family lived, and go to Ocean Beach or to La Jolla and to snorkel and fish and just have an incredible time in the ocean. And that may be one of the reasons why he decided to become an undergraduate at UCSD, and he naturally fell under the spell of the benthic ecology group at Scripps under Dr. Paul Dayton, who many of you will be familiar with. And he worked as a volunteer and then actually as a student assistant. And when he got his BA from UCSD, he was offered the job as a diving technician, and he spent 4 glorious years diving in Southern California. You'll probably begin to realize I'm very jealous of his career. And then during this time, he was thinking about graduate school, and it was the famous or infamous La Nina of 1989, and he jumped into the water, and it was 47 degrees Fahrenheit. So he decided to go to the University of Hawaii instantly. And at the University of Hawaii, he studied the biogeography of Hawaiian corals and the effect of sewage outfalls on the nearshore ecology. And he also looked at the ecology of nearshore invertebrate larvae and how they were dispersed by coastal circulation patterns. And he received his PhD there in the year 2000. And during his time at the University of Hawaii, he traveled extensively in the Pacific and in Asia. And that's where he began to see the really dramatic effects that humans were having on the marine environment. And so he became really very, very interested in doing more research on the impact of humans on these environments. And so that's what brought him back here to Scripps, so he could participate in studies of human-caused disturbance on these marine ecosystems. And he's a project scientist here at Scripps, and he's really ideally positioned to talk to us tonight in his talk, which is entitled "A Place of Their Own, Protecting Sea Life in California." Please welcome me in introducing Ed tonight.
Well, thanks. Thank you. Well, thank you, Nigella. That was a wonderful introduction, and I feel like this is a coming out party. Well, I've been diving around the world quite extensively, and as Nigella said, I've witnessed some major changes in my time, and I'm not really that old, and because of the changes that I've witnessed, I've really gotten more and more interested in what effects we're having. And as part of that, I came back here to Scripps. When I came back, one of the projects I really wanted to work on was finding out how things had changed since I'd been here back in the 80s and 70s when I was just beginning snorkeling. So tonight I'm going to talk about marine protected areas and ecosystems and why marine protected areas are really important for ecosystem protection in general, and how the concept of ecosystems and marine protected areas go hand in hand. This picture that you see up here is actually the kelp canopy, the forest. It's the kelp forest, and it was taken from it was an aerial photograph taken from a plane about 500 feet up, and it's the kelp forest right here off La Jolla. And the kelp forest itself is really a wonderful ecosystem, a highly productive and unique type of ecosystem that's really complex. And I'm going to talk to you about this ecosystem because this is one of the major ecosystems that is the focus of the Marine Life Protection Act in California. And that brings me to the Marine Life Protection Act, which is an act that was passed in 1999. So this talk is very timely because right now the Marine Life Protection Act is being implemented throughout California. And specifically, it's being implemented, just now it's being implemented down here in Southern California. So I'll talk about that process as well. Now this is one of my favorite all-time pictures. This was taken at the Hotel del Coronado back at the turn of the 19th to the 20th century. And they set up these large black sea bass, which used to be really, really common and up till, well, back at that time, starting about 100 years ago, they started getting seriously depleted. And one thing that I'd like you to notice is, number one, how large these animals are. They're huge animals, and they used to be everywhere offshore here. And the second thing I'd like you to notice is how big their mouths are. And these guys have such a big mouth, they can eat just about anything. And because of that, they're very important predators. And for a while, they were all but gone. They're coming back now to some extent, but when a predator like this is all but gone from its ecosystem, the function of that ecosystem changes dramatically. And I'm going to try and hone in on that point several times today and talk about how protecting the ecosystem as a whole is very important, and protecting individual species is as well. So there'll be a convergence of those two issues tonight. And so first I'm going to talk about this concept of ecosystems and how marine protected areas go hand in hand with ecosystem protection. And then I'm going to specifically address the California Marine Life Protection Act. And then I will talk about the work that we've done here at Scripps about researching how effective our little reserves have been here that we have now, that have been in place for decades now. And then where reserves should be if you're going to make ecologically meaningful reserves for the implementation of the Marine Life Protection Act. The first thing I'd like to talk about is the concept of ecosystem. And this is a really important concept because first I'll define what an ecosystem is. An ecosystem is a set of species that intricately and complexly interacts with one another in what's called a characteristic physical setting. And by characteristic physical setting, I've got two examples here. I've got two very characteristic physical settings in the marine realm. We have kelp forests, where the physical setting are temperate latitudes, cool waters, and there's lots of nutrients. So this is a very productive system, and the kelps themselves are very productive, and they depend on lots of nutrients. And it just so happens that the biogeochemistry of the ocean means that there's lots of currents in the cooler waters, and lots of nutrients in the cooler waters, and very few nutrients in the warmer waters. Now the characteristic natural setting for coral reefs is just the opposite. They're more tropical, lower latitude it's a lower latitude setting, and there you have warmer water and poor nutrients. So that characteristic physical setting sets up the sets of species that have evolved and have adapted to those environments, and they interact with each other. Both systems are highly complex. Both systems are highly productive. One depends on a lot of input from nutrients. Another one depends on a lot of recycling as well as inputs. Now, for ecosystems to function within a box where there's not dramatic changes, there has to be something, some stability about them. And in nature, nothing's really stable because the most natural thing about nature is it's highly dynamic, highly changing, constantly. Anybody that's seen El Nino and La Nina years knows that's a very good example. There's also even much longer cycles. But for the stability of ecosystems to persist, there needs to be biological integrity, and the factors that affect biological integrity really need to be in place and not changed. And those factors include species richness, which is the number of species that an ecosystem or a community has, as well as the diversity of species within that ecosystem. And diversity is a little bit different than richness because diversity tells you how well spread out in numbers and biomass the ecosystem is. Richness is simply a number, whereas diversity tells you how even those species are spread out. The more species you have in an ecosystem, that will actually ensure that there's maximal resource use within that ecosystem. So all the production within that ecosystem is utilized, making it as productive as possible. And the other thing is that the resources, the energy within that system is retained within the ecosystem. On the other hand, species diversity, when you have more species that are evenly represented by several different groups, that buffers the risks from environmental changes, things like cycling El Niños, cycling ocean climate. And it also decreases the probability of invasions because we transport species around the planet from here to there, and the effects can be quite devastating, and also disease. So the take-home message really is for biological integrity to be maintained, if it's high, then the ecosystem is resilient to disturbance and to the cycling. And the way we can tell how the integrity of a biological ecosystem is what species occupy that system and how the ecosystem functions. So the species that compose it and the functions within it that make the community structure. Now, why do we care about stable ecosystems? Well, aside from for most normal people, think, well, yeah, we want them for aesthetic value because we want to be able to appreciate them. Who doesn't appreciate a beautiful coral reef or a kelp forest? But aside from those, there's things that ecosystems provide us that are very important. And I'm going to give you some fairly extreme examples, but one example is oxygen. The ecosystem provides oxygen through the process of photosynthesis, and we need that oxygen to breathe. And if it wasn't for the oxygen that was produced in the ocean and on land, we wouldn't be here. We depend on the ocean for recycling our waste. We dump sewage into the ocean, and the ocean has to dilute it, has to deal with it chemically and biologically, and also there's the thing called the food web and the microbial loop where things are degraded by microbes and recycled into plant nutrients. So that's very important. It's a very important ecosystem. The ocean also provides us food, and bees pollinate our fruits and our vegetables. And of course, aesthetics. The ocean is very important aesthetically, as I mentioned before. So we really must sustain our ecosystems for us to be sustained ourselves. So it's very important. But if you look back at the history of man, let me get the pointer here. This chart, I love this chart because it shows the history of man from over the last several tens of thousands of years. On this graph here. So this is a log scale graph in time up to the present up here. And the first thing to notice is that there's been dramatic changes within the last 100 years in several things. And one of those, the biggest thing is the human population has grown dramatically in the last 100 years. We started out at just over 1.5 billion people here, and now we're up to over 6.5 billion and growing. And what's allowed that population growth is really the development of technology. And I've got a couple examples of what technology has helped, or the consequences have been in the ocean. Here we have the Industrial Revolution, where things really start to take off. And then what a lot of people call the start of the Great Acceleration after World War II, when population growth and a lot of these processes here that are represented by curves just take off. And in terms of impacts in the ocean, a couple of big things happened. This happened in about 1913, where two Germans figured out how to fix atmospheric nitrogen, or just nitrogen, into a form that was available for plants as fertilizer. And this is a very important process in world agriculture. And in the process of fertilizing all our fields, the ocean ends up getting a lot of this excess nitrogen, and that's causing what we're having now in regional areas like the Gulf of Mexico. We're having anoxic areas and dead zones in the ocean as more and more of this nitrogen gets out into the ocean. And then later on in the 50s, after World War II, the large-scale factory fishing really started to take off at that point. And so here we have ecosystems here that are cruising, for the last tens of thousands of years along, and then we're really part of the ecosystem and really limited by it. But then our technology allows us to break through, and we're having dramatic effects on everything in the planet right now. So we really need to start worrying about what we're doing to our ecosystems, especially our marine ecosystems. Now, the impacts on marine ecosystems include pollution, not only the nitrogen that I was talking about earlier, but other chemicals, as well as thermal pollution. There's lots of different types of pollution. There's also atmospheric deposition that is really important in the ocean. And as I mentioned before, we're having the effect of bringing species all around the world from other areas where these complex ecosystems have evolved and adapted to one another. And we take a species, a totally foreign species, and introduce it accidentally or purposely into another ecosystem where it can have dramatic effects because it's not adapted to that ecosystem. We also destroy habitat in the process of building our piers and wharves and armoring our shorelines, we've destroyed a lot of habitat. Probably the most important habitat destruction that we've done is we've destroyed about 90% of the wetlands in the world. And the wetlands are very important habitats for things like little fish that, the larval forms of fish that are very important, that they live in there during their early life stages, and lots of them come out to the sea later. We've also, in terms of the atmospheric carbon dioxide increase, we're acidifying our oceans, and so we're having dramatic effects. We're actually measuring more and more acidification in the ocean. And in terms of harvesting resources, which is really what MPAs are about, we've depleted fisheries by a substantial amount to a large extent around the world. We've been at capacity worldwide on a fishery basis for about the last 15 to 20 years. And we're about 2/3 of fisheries in the world are at capacity, over capacity. So we're really stressing the ocean globally. And then bycatch is another issue. Bycatch can be really destructive because when fishermen are fishing for a particular targeted species, if they actually end up catching, in the process, they end up catching a lot of other species as well. And a good example is trawling for shrimp. Up to 90% of the biomass that's hauled in shrimp trawls is discarded by fishermen because they're just after the shrimp. Another example, another thing that we've been doing, and we've been destroying vital habitat. And vital habitat includes areas that are both geologically, habitat that's geological as well as biological. And some of the biological habitat takes hundreds of years to recover from. So we're doing that more and more with our destructive fishing practices. And we've also witnessed from the effects of our overfishing have resulted in fundamental ecosystem change in many areas of the world. And I'll give some examples in the following slides. Okay, so this is a global map of the world. And these two researchers, Myers and Worm, pored over Japanese longline fishing records for years. And they came up with this picture that they published in Nature. And it shows basically that what these colors indicate is how many fish have been caught per 100 hooks in that season, in that year. And this is 1952, 1958, 1964, and 1980. And there's a pretty dramatic difference between 1952 and 1980. We're finding fewer fish, and we're finding them, and we're going over to more parts of the world to find them, but we're finding fewer and fewer fish. And this happens to be the case. This is billfish and tunas and marlin. So these are the typical animals that are the pelagic animals that are caught in the longline fishery. Another good example, and this is probably the best example in a large marine ecosystem of whole-scale change. And this is the continental shelf off of Nova Scotia. It's called the Scotian Shelf. And for hundreds of years, there are populations of cod and haddock, groundfish basically, that persisted. And they're quite healthy populations. And then starting in the 60s and 70s and then in the 80s, there started to be dramatic decreases in abundance of those animals. And those animals, like those fish that I showed you earlier, are really important predators in the system. And when they're removed, then that releases other animals that they feed on to grow in number really rapidly. And that happened. That was actually observed. That happened for pelagic fish, the fish that eat zooplankton. It happened for shrimp, who also eat zooplankton. And it happened for crabs. So all these lines represent the upward trajectory of the biomass represented in those groups. And the consequence of that is, so you have a dramatic decline in groundfish, an increase in these zooplanktivorous fish, and the result is that zooplankton, large zooplankton, the ones that they target, have dropped dramatically in abundance. And the thing about zooplankton is that they eat phytoplankton. And when you drop the zooplankton abundance, then what happens is the phytoplankton has come up really large, has come up to really high levels compared to historical levels. I mean, that's almost a factor of 3 or 4. So that's a profound fundamental change, and that's brought on by this huge, large-scale fishing. Kelp forest is a good local example. Sea urchin. This is a kelp forest being inundated by a front of urchins heading their way. Sea urchins typically live back in little hollows and little caves and things like that, and they depend on the kelp sloughing off at the surface and then being pushed around by the surge, and they'll kind of stay put as long as they're getting enough of that drift. But for some reason, if there's a lot of urchins suddenly, like there's a sudden recruitment pulse, or if lots of urchins migrate into the area, they'll start coming out because there's not enough drift to keep them at bay. And then they'll start coming out, and like a plague of locusts, they're quite capable of mowing down the kelp forest. And what we've done effectively is we've limited the control on sea urchins throughout Southern California because we've fished out the larger lobsters, which are important predators of the sea urchins, as well as the California sheephead. And this is the mouth of a California sheephead. And those are very important, and they've been fished down quite dramatically over the last 30 years. We still see them out there, but they're smaller animals, and they're not capable of taking on the bigger urchins. So that brings me to marine management. So part of the reasons that all this has happened is our approach, and this is controversial, our approach to fisheries management. We've typically done it kind of in a piecemeal and not an ecosystem holistic fashion. We've addressed things we've focused on single species and not how the species interact. And both ecologists as well as fishery managers are talking about how important it is to actually deal with management in a more holistic fashion. So more of an ecosystem-based management. And I talked about that previously. It's a kind of a blend between traditional single species management, which this is a typical curve of what you see. These are landings for the red abalone. So by focusing on individual species, their biomass and their landings, as well as the complex interactions that are going on in an ecosystem. And the best way to protect an ecosystem is really to protect it in its entirety. So you can apply the traditional rules throughout the oceans, and then you can also use this ecosystem-based management, implementing marine reserves where the take is limited or restricted completely, so that the blend allows these ecosystems to recover in terms of the numbers of fish, the size of the fish, and the overall resiliency of the ecosystem itself. Now here's a couple of columns about what types of traditional management there is and what MPA, what MPAs really represent. Single species management has really kind of focused on this thing called maximum sustainable yield. And the idea is that if you have an unfished stock, you have a certain amount of production going on. But then if you fish it down a certain percentage, you can actually increase production of that. And that's what it's a tool that fishery managers use to kind of target how much fish should be extracted. If you fish too much, then you go down towards depletion, and then the whole thing's shot. And we've done that. Lots of species are now at the far end of that curve. And the problem with maximum sustainable yield is that it's, in theory, it seems nice, and it still is controversial, actually. But in the face of changing ocean cycling, in terms of changing climate and, in these different cycles, this is the El Nino, La Nina cycle. How do those species respond to that, to those cycles? They respond quite complexly. And if you're really focusing in on just the maximum sustainable yield, there's so much dynamism in that system that the problem is you overrun your mark typically, and you have to, so maximum sustainable yield is kind of inherently incapable of dealing with that with the dynamism in the ocean. The other thing we have season limits where parts of the reproductive cycle or periods when the fish or other animals are doing things that are important for maintaining themselves, they close those seasons to fishing. Certain sizes are limited because they want certain animals to reach size so that they've at least reproduced once. There's gear restrictions, method restrictions, and quotas. Quotas are for single species, and what happens when a quota is reached, there's kind of a thing called a total allowable catch, where people actually end up getting a summary of all the fish that have been caught for that species, and the managers will close it if the threshold has been breached. Now, on the other hand, marine protected areas, we have the approach is more of a holistic ecosystem protection, and the areas are protected as an ocean wilderness in some cases, like a national park in the ocean. And one could argue, too, that MPAs are also a traditional tool, because going back hundreds of years, Polynesians actually used marine protected areas to sustain their local reef fish populations. And they knew back then that if they overfished them, their fish would be gone and they wouldn't be able to sustain themselves with that resource. So now that I've talked about what the ecosystem and management issues are, I'd like to talk about what MPAs do generally. The first thing they do is they protect critical parts of characteristic habitats. Remember that thing I talked about, characteristic habitats, before. It's very important for some geological formations, some oceanographic, some bottom types, and some oceanographic circulation features to be protected, because they're very important for some species. And going hand in hand with that are in terms of when MPAs are set up, we've actually seen the densities and sizes of individuals increase dramatically within the reserve, as well as increasing outside the reserve as well, as a result of spillover. And inside the reserve, as the individuals grow larger, reproductive output increases dramatically. And here's an example for the California sheephead. On the bottom axis, this is length, and this is the weight of the ovaries in the California sheephead. This is work that was done by Bob Warner back in 1975. You can see it's not linear. It's highly nonlinear, and most of the reproductive output occurs at the very large sizes. So if you're fishing down these species dramatically so that only small ones are left, you're really reducing their reproductive capacity. And there's also evidence lately coming out that the condition of the larvae is much better that are produced by larger animals. And that's very important, because the mortality rates of some of these the larvae are very, very small. I mean, the mortality is great, the survivorship is small. So that if someone puts out 1 million larvae, the condition of the 1 million larvae from the larger animal are going to mean that a higher percentage of that will survive and recruit into the fishery. And then the idea that individuals will spill out due to limited resources within the reserve. As the individual densities or species densities increase, resources become limiting inside the reserve. And as a byproduct of that, they start to spill out. They start to forage over larger areas. And then finally, the idea that these marine reserves actually seed areas outside reserves with larvae. So again, there's this massive increase in reproductive output that's then seeding areas outside. And these guys, this is a great schematic of some larval fish. You can see that what they look like. But lots of these species are planktonic. They're larval for several weeks, and so they have the capacity to drift pretty far. Now I'll move to what the general goals of marine protected areas are. The first is really the conservation of biodiversity, which I said earlier was really important. Critical habitat and ecosystems as a whole themselves. And then they're also designed, or they're also used to address fishery conservation, increasing larval subsidies and spillover to non-protected areas. And they're important for protecting critical life stages and processes. And they're insurance against catastrophe. If there's an oil spill, for instance, and you have a network of marine reserves, and animals inside a reserve are extirpated from that one area, then the fact that larvae can disperse to that reserve fairly quickly, or adults can migrate from other reserves, then the system will recover much more quickly. And finally, here we have, and then really, because over my lifetime, I've never really seen what these sea ecosystems look like when you have all their functioning parts in them. And so by having marine protected areas, you can actually finally fully address what that ecosystem structure was back a long time ago. And finally, they're important for our cultural heritage. Where would we be without a Yellowstone? Don't we need some Yellowstones in the ocean too? Okay, now I'd like to move on to how effective MPAs are. And I'm going to first talk about inside reserve effects. And this is a global picture of how reserves have been effective over the last 20 to 50 years. And this was a study put together by Ben Halpern in 2003, where he surveyed He took 89 studies and he looked at what the effects were of marine reserves. And he found that both density, biomass size, and diversity was significantly higher inside the reserves when you look at them as a whole. They're very important. And this is inside reserve effects in Southern California. In 2003, in the Northern Channel Islands, a set of reserves were established as a result of the depleted fisheries that were being up in the Northern Channel Islands. There's been lots of urchin issues and abalone issues and declining stocks. And so it was independent of the Marine Life Protection Act. These reserves were established in 2003, so they're 5 years old. And as a result, in the last, just recently, researchers at Santa Barbara came out and looked at what the differences were in fish densities and invertebrate densities inside and outside of reserves. And we find that targeted fish biomass was greater inside the reserve by a factor of about 1.7. And fish were significantly larger inside those reserves. And invertebrate densities increased by a factor of about 1.4. And that's Jen Cassell. And then also the community, there are pretty strong community effects as well. These are the fish that eat other fish, and these are just general carnivores. You can see the community structure inside the reserve is much different. There's many more piscivorous fish outside the reserves than inside. Some global examples. Okay, so that was inside-outside comparisons. Here we have adult spillover, and there's been some good examples. Probably the best examples in the literature are from Santa Lucia in the Caribbean, where a reserve was established back in the 90s, and the fish biomass tripled inside the reserve, and it doubled in adjacent fished areas. So there's a good example of spillover. In Cape Canaveral, because of the space operations there, lots of the coastline, 40 square kilometers, was closed to fishing, to all access in general. And as a result of that closure, over the next, since 1985, many of the large catch records for drum and sea trout have come from the areas that are adjacent to that reserve. So those are good examples of spillover. Another example is in the Philippines, Apo Island, where there was spillover of large fish from the no-take reserves into areas that fishermen could harvest them. And probably a really good example of spillover is in the Georges Bank off Massachusetts here, where back in the 90s, 3 areas were closed to fishing completely, to scallop dredging. And scallop dredging was going on for decades, and it's quite destructive. But anyway, the 3 areas were closed, and they were closed for only 4 years by the time that they decided to start looking at what the effects were. And within a short period of time, the scallop densities increased by a factor of 14, and scallops grew larger than people even thought possible. People had never witnessed scallops growing that large in these closed areas. This, by the way, is the closed areas, these lines here. And these little dots represent fishing boats that are tracked by GPS. So they're fishing, quite clearly fishing the edges of the reserve. The other thing that's neat is egg production has really increased in those areas because of the large size animals and the increased density. On the other hand, for some reason, that increased egg production hasn't yet translated into higher production for that. So there's a lot of research going on as to why that might be. But clearly, there's larval spillover going on, and these guys are fishing that quite well. Here's a local example of spillover. We have some data that we've just gotten analyzed where we're looking at how fishermen that fish lobsters off La Jolla and Point Loma are, what their patterns of fishing are. And what you see here is the California spiny lobster, and this is the edge of the reserve off the cove. And most of the season, the fishermen are fishing up in the northern half of La Jolla because it's really good lobster habitat. But then by the latter half of the season, it's a 6-month season, so by about December or January, they're primarily fishing the edge of the reserve, catching that spillover. That's quite a clearly established pattern now. So now I'm going to switch gears and not talk about marine reserves necessarily and their effects, but talk about what's happened in California and the Marine Life Protection Act. This was a photo that was taken in the 1930s in northern Baja California, and it just shows how much fishing effort was going on back then. It's just a dramatic picture. It speaks for itself. To give you a brief idea of what's happened in California over the last few hundred or so years, these are quotes from journals that I've looked through, as well as from fishery reports, fishing logs. By 1870, it was already pretty apparent that abalone were being overexploited fairly rapidly. And as early as the 1920s, nets and barge fishing were dramatically reducing many of the species of fish here in Southern California. And I've got a picture of barge fishing that I'll show you in the next slide. But each generation has its own little horror story. And then with the advent of scuba and the affordability of outboard engines and the development of LORAN and GPS now, there's been a second wave of fish depletion and abalone depletion. And this depletion wave in the 50s actually coincided with a regime shift in the ocean. So there was not only overfishing going on at that time, very early actually, but there was also an ocean climate change that reduced the fish themselves. So it's kind of a double whammy, if you will. And then in 1994, one of the most important things that's happened in the state is that gill nets were restricted. And actually, that's probably one of the best things that we've done in our coastline, because since that has happened, black sea bass are becoming more numerous, white sea bass are becoming more numerous, and there's many other different species of fish that have become more numerous since the gill net restriction went into effect. And then more recently, since the mid-90s, live fish trapping became problematic, has become really problematic. Now here's a picture taken off of Point Loma in the 1920s, and this is what's called barge fishing. And this was the practice of taking old sailing hulks and dismasting them, anchoring them offshore, and then ferrying fishermen back and forth from the shoreline to go kind of use these barges as fishing platforms. And this is an intense amount of effort as early as the 1920s. So that's a dramatic amount of effort, in fact. So where are we now? The status of several things have changed in a relatively short time, over the last 100 years. Abalone are so uncommon in Southern California that you can't fish them recreationally even. Rockfish areas have been closed. Large areas in federal waters have been closed as essential fish habitat to bring back rockfish populations. Rockfish are particularly susceptible to overfishing because they're relatively sedentary, they're slow growing, and they're slow to reach adulthood, reproductive age. And there's also lots of quotas in effect, and it's very difficult to actually know as a fisherman which species you can target, because they're always changing. As the year progresses and the quotas are reached, then those particular species are either closed or different depth zones are closed. So there's lots of different rules going on. We have important predators that I mentioned before, like the California sheephead, are much less abundant, and they're smaller, as in the case of the lobster. There's still lots of lobsters out there, but they're much smaller than they used to be. Their ecological roles are very different because of that. So they can't really have the same predatory impact that they have as large animals. And so you can only get that either by having really good single species management and keeping the larger individuals from being fished, or you have to set aside marine reserves. And then finally, pelagic and highly migratory species are being fished at or over capacity and throughout much of the state. So as a result of what's happened, the Shelley Bill was passed in 1999 by the California State Legislature. And it basically calls for the protection of habitats and ecosystems, the protection of diversity, which, as you recall, is very important for the integrity of the ecosystems, to enhance recreation, and to serve as baseline for scientists to understand how pristine ecosystems actually function, and for fisheries conservation. And in this role, conservation, the word conservation really means in terms of fishery yield, increasing fishery yield, or making fisheries sustainable. And this law applies only to state waters within 3 nautical miles of the mainland. And the first go-round what happened was the MLPA was passed in 1999, and I call it MLPA version 1.0. And it called for the establishment of a statewide reserve system to be in place by 2001, which then lapsed, went to 2002. And then because, for several reasons, mainly because there wasn't really money to implement it, the whole effort was stalled by Governor Schwarzenegger, and it was kind of temporarily abandoned. But then in came the Resources Legacy Fund Foundation and some other nonprofits that got together with the Fish and Game and decided to resurrect and fund the implementation of the MLPA. And now it's been resurrected as version 1.1. It's called the MLPA Initiative, and it's supported by this public-private partnership. Now, the first go-round really was kind of a top-down process, and what it was scientific panels and government agencies and managers got together and said, okay, this is where we're going to protect, and we're going to protect in these networks. And then they went out to the public and had meetings up and down the state and said, this is what we're going to do. You know, it's kind of like government stepping in and saying, we're going to do this. And there was a lot of backlash against that approach. And you know, you can understand why, clearly, because it's affecting a lot of the stakeholders that depend on the ocean for their livelihood. So with that in mind, the second version, the MLPA initiative, was really has become more of a bottom-up approach. And it still gets guidance by scientists and by managers, but the central role here are stakeholders, people that they make their living off the ocean, or they're very interested in keeping the ocean pristine. You know, they're conservationists, they're fishermen, they're a whole wide diversity of people that have some important stake in the process. And the idea is for these people to come up with reserves and networks throughout the state, based on scientific principles and management principles. And then what happens is those plans, those proposals then go to the Blue Ribbon Task Force that is kind of a administrative group that kind of are a liaison between the Fish and Game Commission, which make the final decisions on where these things are going to go, and the regional stakeholders. So there's a lot more input from the bottom in this process for this with the version 1.1. And then it's going to be rolled out in 4 phases. As opposed to the first phase, it was being rolled out all at once. This is being phased in 4 different phases. Actually, there's a 5th one here, San Francisco Bay, that's not listed. But the reserves as a network have been set up in Central California as of last year. North Central California is underway. The regional stakeholders groups have already finalized their proposed plans for where reserves should be placed in North Central California. And Southern California is just now getting started. So this is a very timely issue down here in Southern California. And Northern California will be addressed after Southern California is underway. And I missed a slide here, but this is an important concept. The idea, here's the continental shelf off of the coast of California. Here's Southern California, Point Conception. And here's the borderlands of Southern California, which are quite extensive, a series of hills and basins and ridges out until you get out to this patent escarpment well offshore. So it's very different from northern and central California, where the shelf is much narrower. So it has the ecology, the ecosystems of these different areas are very different because of that. But the idea is that you want to, the MLPA, the reserves are going to be set up as a part of the MLPA are going to be set up as networks. And so that the animals and plants, or specifically animals mostly, the larvae and the adults can communicate among these different habitats in a reserve network, in a network fashion. Okay, and these are the actual resulting Central California marine protected areas as a result of that version 1.1 I talked about earlier. What happened was the red areas ended up being state marine reserves where all fishing is excluded, and that included about 7% of state waters in that area. And then the blue areas are called conservation areas, which are areas where there's some level of extraction allowed. So there's special rules in those areas. So we ended up with about 7.5% of the waters being completely protected, and about 17% being fully protected or being in these marine conservation areas or marine parks. State marine parks are areas where commercial fishing is excluded. State marine conservations are areas where both recreational and commercial fishing is allowed in specific forms. So that begs the question, what's important when you want to design reserves? It really boils down to what species can you protect with these reserves? And it just so happens that you really can't protect the more migratory species that well unless you can protect their spawning areas. So most of these reserves are being aimed at animals that are a little more sedentary than the more mobile, highly migrating species. And it boils down to those habitat and locations are the most important that people are focusing on happen to be hard bottom. Hard bottoms is very important for rockfish because the rockfish are very susceptible to overfishing. And then it's not clear how big you should make it, how big each reserve needs to be. And if you're going to have networks, where are you going to put them and how many are going to put them? And that's the role of the scientific advisory team, is to come up with guidelines, kind of rules of thumb, if you will, for how big these should be, how many there needs to be, and how specifically you place them spatially so that they network with each other successfully. And then the stakeholders also take into account the socioeconomic factors. My final concern about the MLPA is enforcement. And this is a great slide. But the MLPA, as I said before, was really passed without really any money to enforce it. And so for this to be successful, you really have to convince everyone that these things are good, because the people that are out there the most are the ones that are going to enforce these things. They're people that are going to be reporting. The Fish and Game is not going to be able to be out there enforcing these things on a regular basis. They just don't have the resources. So for this thing to have any chance of success and for them to be effective, there really needs to be peer acceptance and peer enforcement of them. And finally, I'm going to conclude with the marine protected areas in San Diego and some of the work that we've done in terms of how effective our reserves have been and where we should put reserves in San Diego as part of the Marine Life Protection Act. This is a picture of Jimmy Stewart, who's a dive safety officer here back at Scripps. He was the first fellow back in the 50s that came up with the first set of protocols for diving safety at Scripps. And this is a typical haul, according to Jimmy, back in the 50s, just snorkeling right outside the children's pool. The first thing you know, anybody that knows anything about lobster now, first thing you know is these things are huge compared to what you see out there now. The fishermen are so efficient at trapping every legal sized animal that the only place that I see these are back in the back corner of our reserve here and down in the submarine canyons where the fishermen aren't fishing. Otherwise, these guys are rare. And if a diver sees that, they'll probably have a heart attack underwater. Since you're from here, you're probably familiar with the San Diego La Jolla Ecological Reserve. It's a fully no-take marine reserve that extends from Alligator Head out to a portion of this kelp forest and into shore here at Scripps. And one of the most important things about it is it really is a marine reserve that was set up to protect the diversity of habitats. It protects the La Jolla Submarine Canyon. There's a head of a submarine canyon that is right in this area, and actually the lion's share of the reserve protects the head of that submarine canyon. It protects a little bit of kelp forest, and it protects some really important boulder reef habitat out here where abalone used to really be really abundant and used to have really important spawning aggregations. And it also protects the sandy shelf, the sloping sandy shelf that goes out to the edge there. And when they set it up, it was really set up in 1971 as kind of a real mix of motivations that weren't really explicit in anything that I could find. And by talking to lots of people and kind of reading through the print, I just basically settled on the fact that it was set up where it was set up to really protect the canyon rim habitat. On the rim of the La Jolla Canyon are gorgonians and other biological structures that are very important for important as nursery habitats for some of these rockfish. And a lot of the squid fishery, the nets were actually dragging the bottom and damaging those habitats irreparably. There's also a skiff fishery off here in La Jolla shores that was hitting the grouper out here. And I know Jimmy Stewart and Connie Limbaugh, who was a really famous fish biologist back at Scripps back in the 1950s. There were broomtail groupers in mass in this area, especially out here. And they really wanted to protect that area from the skiff fishing fleet that was coming out of La Jolla shores. But by the time that the reserve got established, the groupers were already gone. And finally, this area here, like I said before, is really important abalone habitat, and it was set up. The reason that this area was included was it was to protect the abalone populations there. Now, when you look at the same kind of comparisons that I presented before, you look at what was going on inside the reserves, and you compare it to comparable habitat inside the reserves, and we look at boulder reef communities, submarine canyons, as well as the kelp forests, we find clearly for all these things, red urchins, rock scallops, California sheephead, green abalone, lobsters, and vermilion rockfish, that there were dramatic effects of protection. For many of these species, they're all in higher densities, and for many of them, they're much larger. Red urchins were much larger. The mode for the average, the size, the legal size for red urchins is about 83 millimeters, about that big. And that is, when you go anywhere and look at the size distribution of red urchins, they're really at 83 millimeters. And you go inside these reserves and they're up to 110, 120 millimeters. And vermilion rockfish are quite abundant in some of those areas. So the reserves, that little reserve has been successful somewhat for the more sedentary species. And it's been very important for green abalones. Even though green abalones are now protected, and they have been since the late 90s, the reserve kind of has had a legacy effect because it protected abalone fishing before that, prior to that, the 98 closure. And we can see that the abalones are more aggregated inside the reserve than outside the reserve. This is how many abalones are in aggregate. And why this is important is because abalones are spawners, and they have to be close together to reproduce. There has to be a male and a female within a few feet of each other, ideally within a few inches of each other, to successfully reproduce. The female will shoot off her eggs, and the male will shoot sperm into the water, and they meet. They have to mix, and the eggs are fertilized. And if there's no aggregations, even if you find abalone out there, they're effectively sterile. So when you look at that remnant population of green abalone inside the La Jolla Reserve, they're really important if we're going to get our green abalone back here. And so we also did some work in the La Jolla, throughout the hard bottom habitats in San Diego County, to look at what areas really need to be protected. Here's the marine reserve, the La Jolla Marine Reserve. Here's the submarine canyon. And what we did is we went and enumerated what these different types of habitats and how they were distributed throughout the hard bottom in San Diego County. And each one of these colors represents a different type of habitat. And associated with each one of these habitats is a different affinity for several different species of fish and invertebrates as well. So this is really spatially explicit information that can be used to go directly into reserve design. And it still begs the question, though, okay, we know how it's kind of arranged, but we don't know how big they should be, and kind of if we're going to make them a certain size, where should we put them? This kind of this kind of a map addresses those questions. Just so happens that the yellow habitat and the blue habitat are really good areas to protect. And northern La Jolla doesn't really have, while northern La Jolla has a high diversity, it doesn't really have a lot of those really good areas. And so what we did is we made up an algorithm, a little mathematical expression to kind of take into account how those habitats were distributed, what the species were, what the species affinities were for those habitats for a set of 20 different exploited species, and how far those species move around. And we kind of randomized a reserve, kind of like seeding a reserve, like you randomly pick a box, you say, okay, well, if we start a reserve there and grow from the seed, how effective is that reserve going to be? And we've done this for all the hard bottom habitat in San Diego. And an example in La Jolla is this was published in 2006, and this is a map of the hard bottom. This is the red area indicates hard bottom, and the blue areas indicate softer bottom. The white areas have not been surveyed for that type, for the bottom types. And this represents the kelp bed, and the darker color represents the more persistent area of the kelp forest. And we came up with, based on that algorithm for La Jolla, that the southern half, or the southern portion of La Jolla would be better to protect than extending the current reserve out around the corner from La Jolla, from Point La Jolla. And finally, as part of our research, we doubled up with the anthropology group here at UCSD, and we're trying to get an idea of what the response was, or what people's attitudes were towards the reserves, and what their knowledge was towards those reserves. And one of the questions we asked, and I like to show this a lot, is who owns the coastal resources? I'd like to say it's my daughter here. But we came up with answers ranging from no one, the government, fishermen, the god or gods, Mother Earth, and everyone. And I'll leave you with, what do we want to pass on to the next generation? Do we want these reserves to try and recover some of these fully functioning ecosystems? Do we want to convince fishermen that these things will probably do them good in the long run? The future is wide open, and it's kind of interesting now for everyone because everyone can get involved in this Marine Life Protection Act. Thank you. The question is, are they trying to reseed areas once they've been established? And the answer is no for the marine protected areas. But there's also been lots of seeding efforts with abalone and some fish. And most of those efforts are pretty much unsuccessful. There's been a long history of abalone reseeding, and the mortality rates of these animals are really, really small. A fish example would be white sea bass, which are being grown out by Hubs, SeaWorld, and then being grown to a certain size by different environmental groups, and then being released. And the jury's still out on how effective that is. But those are examples of it. But with relation to actually seeding marine protected areas, there's not been much of that work at all. The question is, this lady's from the Pacific, I guess you perform interviews? Surveys, okay, you do interviews of recreational fishermen. And the question is, would it be kind of acceptable to set large size limits on them? And I think yes, and that's called slot limits, and that's been successful in some areas. And even sliding those MPAs around, year to year has been successful in other areas. So that's another option, although that option is very difficult to enforce. Thank you.
And thank you so much. I'm sure he'll be glad to hang around and answer questions.